Hi, welcome back. In the previous module, we got an understanding of the business benefits of automated tests. In this module, we'll look at automated tests in a little more depth and understand the different types of automated tests we can write. So we'll start off in this module by looking at the different types of automated tests we can write. We'll learn about unit tests, integration tests, subcutaneous tests, and functional user interface tests. We'll see how each of these types of tests offer different characteristics when it comes to test breadth or test depth, and we'll learn about the different logical phases of an automated test. We'll get a brief overview of mock objects and how we can use them to isolate the code that we want to test. And we'll learn how data-driven tests can reduce the overall amount of test code we need to write. We'll learn that we can make our tests business readable so we can bridge the communication gap that can often occur between the development team and the business or stakeholders. So if we have all of these different types of tests available to us, how do we know how many of each type of test to create? We'll learn a couple of different ways of thinking about this. So we'll learn about the classic testing pyramid model, and also how we can go beyond this initial pyramid model and decide which type of tests to create. Finally, we'll round off this module by looking at a few of the characteristics of good automated tests. So let's kick off this module and we'll start to look at unit tests. If we think about the system or the application we're writing consisting of a number of different parts, so in the diagram here, each of these circles represents a distinct part of the application. In an object-oriented language, each of these circles would represent a class. When we create a unit test, it targets a small single part of the application here. So once again, this could be a single class. We're testing this class in isolation from the rest of the system. Unit tests have a number of different characteristics. First off, they're low-level tests. They're focused on the lower-level details of the system. In this way, they're highly focused tests. We're not testing the whole system working together, we're just testing a very small part of it in isolation. Unit tests are generally really quick to execute, so we get really fantastic feedback speeds, which means we can find out very quickly if we've broken something. Because unit tests have a small number of moving parts, it's easy to test all of the parts or all of the paths of the code and get our test code to execute every nook and cranny of the thing we're testing. A unit test may also test more than one thing. So in this example, we've got two classes here, and these are considered a unit for testing purposes. We may have another unit test which tests three classes working together. Or indeed a unit test which is only focused on a single class and no other classes. So how do we decide what a unit is? Well, Martin Fowler has this really great quote. It's a situational thing. The team decides what makes sense to be a unit for the purposes of their understanding of the system and its testing. To describe it more succinctly, we can describe a unit test as testing a unit of behavior. The team defines what these units of behavior are, and we test each unit of behavior in isolation from the other units of behavior in the application. Let's take a look at some pseudocode now to illustrate what a unit test might look like. So first off, we have the beginning and the end of the individual test, and we're naming this test addition. This unit test is going to be testing a calculator. So the first thing we need to do in the test code is actually create an instance of this calculator that we want to test. Once we've got an instance of the thing we want to test, we can go ahead and execute the add functionality, passing in the values of 5 and 2. Once we've executed the add functionality, we can compare the results that we got back from the calculator, and if it's equal to the expected result of 7, we can report this test as passed. But if the result is not 7, we report this test as failed. If this test fails, then the developer can go and look at the calculator code and determine what's wrong. Let's take a look next at integration tests. So if we use our diagram here and draw on an integration test, we can see here that we're testing a larger number of classes working together. In an integration test, these classes may not have the same tightly knit behavioral cohesiveness as with our unit tests. Integration tests may also make use of external dependencies. So for example, this could be a database, reading or writing to the file system, or using some kind of network resource or API. Integration tests can be said to operate at a higher level than our unit tests. Essentially, we're testing multiple parts of the system working together, or to put it another way, multiple units of behavior working together. Integration tests may execute more slowly than unit tests, especially if the integration tests involves external dependencies, such as reading or writing to the database. When we're writing integration tests, it may be harder to test all of the parts or all of the paths of the code because we have more moving parts working together. If we have a look at some pseudocode here, we'll start off with the beginning and ending of the test, and we're calling this test Loan Application Successful. This test is going to involve two different classes. First off, we're going to create a new instance of a FrequentFlyerValidator, and we're just going to call this instance V. We're then going to create a new Loan Application Scorer instance, we'll call this S, and this Loan Application Scorer requires a FrequentFlyerValidator to be able to do its work. So we'll pass in the instance V of our FrequentFlyerValidator. Next, we can go and call the functionality of the Loan Application Scorer, and into this score loan functionality, we'll create a good applicant. If the result of the score loan functionality is equal to loan granted, then this test will pass. Otherwise, if we get a different loan decision, such as declined or referred, then this will fail. If we head back to our diagram here, and we'll just map this dependency, so we've got our Loan Application Scorer class, depending on a FrequentFlyerValidator class. So the FrequentFlyerValidator is a dependency of the Loan Application Scorer. In the previous pseudocode, this could be described as an integration test, but the team could also decide that the unit of behavior here for the Loan Application Scorer also includes the FrequentFlyerValidator, so this could also be considered a unit test depending on the team's definition. However, if this FrequentFlyerValidator accesses an external resource, such as reading valid frequent flyer numbers from an external database, then we could no longer consider this a unit test because we're accessing an external resource. This would instead be considered an integration test. So generally speaking, if the code being tested uses external dependencies, it would be considered an integration test and not a unit test. Let's take a look next at subcutaneous tests. So here's our diagram with our unit and integration tests marked. Let's now go and add our subcutaneous tests. So notice here that subcutaneous tests involve a larger portion of the system. The only portion of the system that they don't cover are any user interface related components. Subcutaneous tests exist at a higher level than integration tests, but they sit just below the surface of the user interface. With subcutaneous tests, we can test that all of the non-UI components are working together properly. Subcutaneous tests are also potentially quicker to execute than automated user interface tests. We'll look at UI tests in just a moment. We may rely more on subcutaneous tests over automated UI tests if the user interface is difficult to test for some reason. One thing to note is that subcutaneous tests sit just below the user interface surface. This means that if we have any business or other logic in the user interface, we won't be able to test this with subcutaneous tests. Unlike subcutaneous tests, functional user interface tests can test the UI components of the application. Notice here that automated functional UI tests can encompass the entire system, right from clicking a button in the user interface all the way down to interacting correctly with a database. Unlike with subcutaneous tests, When we're using functional UI tests, we can test logic that's encoded in the UI components. So with functional UI tests, we're testing as if we were the end user interacting with the application. This means we can be manipulating UI elements, such as typing text into text boxes and clicking buttons in the UI. Sometimes this is known as full stack testing because we're testing right from a button click down to the database. One thing to bear in mind with functional user interface tests is we're testing the functionality of the system. We're not testing how the system looks or feels, so for example colors or fonts or design layout. Functional user interface tests can also be the slowest of all of the types of tests we write. That's because we're simulating typing text into text boxes, clicking buttons and waiting for the UI to refresh. All of these things take time and can slow down the tests. Another thing to bear in mind with functional UI tests is they can be potentially more brittle than other types of tests. For example, if our automated test code is trying to locate a checkbox with a specific name and the user interface is now updated, perhaps replacing the checkbox with another type of user interface element with a different name, then our functional UI tests will no longer be able to find the checkbox and the test will fail. There are, however, testing design patterns we can use with functional UI tests that help to reduce this brittleness. So now we've got an idea of the different types of tests available to us, let's consider the difference between these types of tests as relates to the breadth or the depth of the testing. So on this chart here, the y-axis represents the depth of the tests. So this is the ability to get into all of the low-level nitty-gritty details. On the x-axis here, we've got the breadth of the test. So this is the ability of the type of testing to exercise a wide range of the functionality of the application. So we'll start off here with unit tests. Unit tests are generally the most in-depth tests that we can write. We can get right into the nitty-gritty detail of the individual lines of code in the things we're testing. However, unit tests don't cover great breadth of system functionality. They're limited to small, isolated units of behavior. Next, if we plot integration tests on this pseudo chart, we can see that integration tests offer slightly less depth than unit tests, but they can also offer us greater breadth. While we may not be testing as much detail as unit testing, integration tests allow us to exercise multiple parts of the system working together. Next up, we have our subcutaneous tests. These type of tests can offer us greater breadth of system coverage, but at a cost of the depth of testing. Finally, we have our automated functional UI tests. These can offer us the greatest breadth of system execution right from the user interface down to the database level. However, these types of tests are quite shallow and it's extremely hard to get down into all of the nitty-gritty details of every class in the application. An individual automated test can be generalized into three distinct logical phases. The first phase of a test is the arrange phase. In this phase, we're getting things ready to test. So we're creating new instances of the things we want to test or setting up any external infrastructure or test data. The second logical phase of an automated test is the act phase. In this phase, we're executing functionality of the thing we're testing to produce some response. In the third and final phase, the assert phase, we're taking the response from the act phase and comparing it to an expected value. If the actual result matches the expected result, then the test passes. If we take a look at this code from earlier, our lone application successful code, we can generalize this into these three phases. In the first phase here, the arrange phase, we're getting things ready to test. So we're creating the instance of our FrequentFlyerValidator and the instance of our lone application scorer. In the act phase here, we're executing the functionality of the lone application scorer. So we're calling the score lone functionality here and getting a result back. In the third phase here, the assert phase, we're taking the result from the act phase and comparing it to an expected value, in this case lone granted, and reporting the test as passed or failed. Sometimes when we're writing tests, we may want to isolate dependencies or other parts of the system so we can focus on testing a specific class or subset of classes. So for example, if we wanted to create a unit test, but the lone application scorer here has a dependency on a frequent flyer validator, and this frequent flyer validator needs a database to work, we can't create a unit test here. If we didn't want to create an integration test here, we need some way of isolating the lone application scorer from its dependencies. To do this, we can use mock objects. There's different terminology around this concept, including mocks, stubs, test doubles, and fakes. We're not going to get into the details of these in this course, we're just going to stick with the term mock object. Mocking is essentially the act of replacing the actual dependency that would be used at production time with a test time only version that enables easier isolation of dependencies. If we head back to our diagram, we want to remove the database from the equation. To do this, we also need to remove the real frequent flyer validator from the equation. And we can replace this with a mock version. The lone application scorer here can now use the mock version as its dependency rather than the real version. If we head back to our lone application successful test, notice that the act phase and the assert phase remain the same. We need to make some changes to the arrange phase, however. First off, rather than creating a real frequent flyer validator instance, we're instead going to create a mock version of a frequent flyer validator, and we're just going to call this MV. We can now configure the mock object to behave in such a way as it supports the rest of the test. In this example here, we can configure the mock frequent flyer validator to always validate frequent flyer numbers passed to it. We can now go and create the lone application scorer instance as before, but this time, rather than pass a real frequent flyer validator, we're instead going to pass the mock version as its dependency. When we call the scoreLone functionality of the lone application scorer, the lone application scorer will call into the mock frequent flyer validator. This mock version doesn't require a database, so we can consider this a unit test. One technique we can apply to any type of test is the technique of creating data-driven tests. This essentially allows us to execute a single test multiple times with different test data. So if we have a look at some tests here we've got this test, add positive numbers, and we're testing our calculator instance. We're adding the values 5 and 2 in this test, and checking the result is equal to 7. We can add a second test, add negative numbers, this time passing the values -5 and -2, and checking the result is equal to -7. So now we've got one test for positive numbers and one test for negative numbers. If we wanted to add another test to check mixed numbers, so this time adding the values -5 and +2, we'd have to write a third test. So now in our test code, we've got 3 individual tests, but there's a lot of code duplication. Essentially, the only difference is the values that we're passing to the add functionality and the expected result. We could remove this code duplication by instead having one single test, and this time replacing the hard-coded values that are passed to the add functionality with some kind of placeholders. Here I'm using the placeholders A and B, and in the assert phase, we're checking the result is equal to this placeholder C. Now we can construct a series of test data. Each row in this table will cause this test to be executed with the different values for the placeholders A, B, and C. So the first time this test is executed, A will be 5 and B will be 2, and the placeholder C will be 7. So now, if we want to add new test cases, we can simply add new rows to this test data. If we had 5 rows, for example, then this test would be executed 5 times. This means we don't have to go and duplicate all of this code simply to add additional test cases with different test data. Another technique we can use on top of any type of test, be their unit, integration, subcutaneous, or UI, is the technique of creating business readable tests. Here we've got the business or the client or stakeholders that determine what products are being built. On the other side here we've got the developers or the development team. There needs to be good communication between these two sets of people to ensure that the correct features are built. Sometimes, however, there can be a communications gap between these two sets of people, resulting in incorrect or missed requirements, or even the wrong features being delivered to production. Business readable tests help overcome this communication gap by allowing the creation of tests that exist in the language of the business or client. So why might we want to go to the additional effort of creating business readable tests? First, business readable tests allow us to document the application. The tests describe what the features of the application should be and how they should work. These tests are written in a non-technical fashion in a language the business can relate to and understand. Because tests are easily readable, it helps onboarding new people to the development team, whether they be developers or even QA or test specialists. The specifications as to how the system should behave are documented in a non-technical way, and underneath the covers, this non-technical documentation maps to executable test code. So we can actually execute this documentation in the form of tests. Business readable tests sit alongside the source code. This means they can be version controlled, so our documentation doesn't get out of sync with the actual production code. Because of this, the documentation has to stay accurate and up to date, because if it gets out of sync with the production code, the tests will fail. In this way, we can think of business readable tests as living documentation for the system, unlike, for example, a Word document in SharePoint. Ultimately, business readable tests can result in better communication between the stakeholders and the development team. Because the tests are written in a common language at a high level, anybody can understand and verify the requirements of the system. This means that the correct features are being worked on, and we can reduce the wasted effort of developing the wrong things, or some work making it all the way to production, but with some missing features. Ultimately, business readable tests help ensure that the right thing is being built, and it's being built right. As an example, let's take our calculator add positive numbers test. We could create a business readable version of this test. At the top, we're describing the feature, in this case addition, and then for each test that we want to execute, we describe a scenario. So the first scenario here, positive number addition. Inside this scenario, there's a number of steps. Given I have a new zeroed calculator, when I add 5 and 2 together, then the result should be 7. And we can go and create additional scenarios, for example, negative number addition. This format of business readable tests expresses the requirements in the Gherkin language. Gherkin is a business readable, domain-specific language that lets you describe software's behavior without detailing how that behavior is implemented. Gherkin serves two purposes: documentation and automated tests. You can read more about Gherkin and business readable tests at this link here. So how many of each type of test should we have in our overall automated testing portfolio? One model to describe the relationship between these types of tests is the testing pyramid model. In this model, we have the fewest number of tests at the top of the pyramid here, and at the bottom of the pyramid, we have the greatest amount of tests. So at the top of this pyramid, we have our functional user interface tests. And we have the smallest number of these type of tests in this model. Underneath UI tests, we have our subcutaneous tests. So we have a greater number of subcutaneous tests than we do UI tests. Further down the pyramid, we have our integration tests. So we have more integration tests than subcutaneous tests. And at the base of this pyramid, forming the bedrock, we have our unit tests. So the greatest number of tests we have using this pyramid model are our unit tests. The further up the pyramid we go, the slower the tests become. So user interface tests execute more slowly than unit tests. As we rise up the pyramid, tests can become more complex because we have to set up more moving parts to be able to execute the test. Tests higher up the pyramid can also be more brittle and prone to breaking. The most potentially brittle tests we can write are the user interface tests. And as we move up the pyramid, tests become more broad, and we saw this earlier in this module when we compared breadth and depth. On the other hand, tests towards the bottom of the pyramid become faster to execute, and so we can get the feedback quicker. They become more simple to set up and execute. They can be more stable and resilient to changes in other places of the codebase, but they have a more narrow scope. The testing pyramid can be a great guide if you're completely new to automated tests and you don't know where to get started with the number of tests to write at each level. However, once a lot of experience is gained with automated testing, the test pyramid might be too constricting, so we can use a different set of heuristics to decide which type of test to write. So what aspects of automated tests can we think about if we want to move beyond the testing pyramid? The first thing we can think about is how quickly the tests execute. So essentially, we want to choose tests that allow us to find problems sooner. As we saw earlier in the course, the longer a problem exists for, the more expensive it can be to fix. So here, given the choice between two types of test, if we just had this aspect to consider, we'd always choose unit tests because they execute the fastest. However, we can add some additional aspects here. We want to write automated tests that mitigate risks in the project. So we can choose tests that give us the minimum required level of confidence that the system is going to work as expected once released to production. We could write 20 unit tests that exceed the minimum level of required confidence, or a single subcutaneous test that allows us to meet the minimum required confidence that we need to release to production. If we add a third aspect now, and that's a focus on behavior, or to put it another way, we should choose tests that have a minimum amount of knowledge of the implementation of the thing we're testing. So we want to test the behavior rather than how that behavior is implemented. So using this diagram, the sweet spot for automated testing is the intersection of all of these three aspects. Ultimately, we can sum up this way of thinking about automated tests by saying that we should write the smallest number of tests possible to reach the required level of quality or confidence in the system being developed. Let's wrap up this module by a brief discussion on the characteristics of good automated tests. Good automated tests should be isolated. Basically, this means that one test shouldn't affect other tests being executed. Good tests should be independent of each other, so they should be able to be executed in any order and produce the same results. Good tests should be repeatable and reliable. This means that all other things being equal, they should always pass or fail. Also, an important characteristic of good tests is their maintainability, so they should be understandable and easy to change as required. Overall, good automated tests should add value to the project. If they don't add value, then why are we paying the cost to create and maintain them when we could be using that effort to actually add features to the product that will benefit our users? So that brings us to the end of this module. In this module, we learned about the different types of automated tests. So we learned about low-level unit tests and also what the definition of a unit is. We learned about integration tests that may talk to external resources such as databases, and subcutaneous tests which exist just below the surface of the user interface. We also learned about functional UI tests that simulate an end user using the application. We learned that some tests, such as unit tests, offer great depth, whereas other kinds of tests, such as UI tests, give up broader coverage of the system being developed. We learned about the different logical phases an automated test can have, the arrange, act, and assert phases, and we saw how we can isolate sections of the codebase using mock objects. We learned that we can reduce the amount of test code that exists by creating data-driven tests. And we saw how we can bridge the communication gap between the development team and stakeholders by creating business readable tests that help to ensure that the correct features are being implemented. We learned some different ways of thinking about how many tests to have at each level. So we learned about the testing pyramid and also how we can go beyond the testing pyramid and use a set of guidelines so we don't waste too much effort writing unnecessary tests. Finally, we learned about some of the characteristics of good automated tests, such as the importance of isolation and also maintainability. Join me in the final module when we'll learn how automated tests fit within the wider software development process.